Bell Labs, that at the time was a big thing in the US. And he got quickly after, I think, 5 or 6 years, a professorship in Yale. And he relocated to Harvard in 2005 as a professor, where he stayed there basically till now. The lectures will be, should be engaging. So anytime you have a question, please, the speaker will notice, and me or Martino, so I will cover this part, and Martino will cover that part, will bring you a microphone, because the question has to be recorded and has to be noted. We are gonna stop 10 minutes before the end, so there is some time for additional questions on what you are presenting. So I'm gonna give you a signal when you have 5 minutes left, and I will take care to control time.
So that's 90 minutes, so 80 minutes then?
Yes, that's correct. That's correct. But depending on the amount of questions, I'm gonna tune it. But if there is a normal amount of questions, that's what we are gonna do. So welcome everyone. Please, Subir, you have the floor, and enjoy.
Okay, thank you very much, Jamir, for a very kind introduction. 2 of them, both very, very warm and too kind, so thank you very much. Anyway, so it's great to be here. Yeah, as Jamir said, please don't hesitate to interrupt at any moment. There's many things I want to talk about, but this is a school, and I will try to make everything as pedagogical as possible, except maybe in the last half an hour, 45 minutes will be on current research, things I'm very excited about. So that would be, I have 3 lectures, 2 today and 1 tomorrow, and then a tutorial also tomorrow. So you'll be seeing a lot of me. Okay, so I thought of this title for my lectures here, calling it Planckian Dynamics. This word Planckian entered condensed matter, I would say, through Jan Zanen, who relates to the fact that there are many emergent phenomena in matter which seem to have this remarkable property that some kind of dissipative relaxational time. So we're talking about a system that had its own dissipation from strong interactions. Is of order Planck's constant divided by Boltzmann's constant. So divide by the temperature, and of course Boltzmann constant. That's a fake constant, because if you just measure temperature units of energy, you wouldn't need Boltzmann constant. The Boltzmann constant is an arbitrary definition for temperature. Anyway, so if you forget that, it's just Planck's constant divided by energy is a time. So this is a Planckian time, and it seems to be the basic time that emerges, as I'll show you in many condensed matter experiments, when there are very strong interactions. And what's also emerged in the last decade, but I will not talk about, through very different developments, if you look at black holes. So for example, if you have 2 black holes that merge, as LIGO has seen, they have some very complicated shapes, but eventually they merge and become a perfect sphere. And taught us that a black hole is also a system in perfect with a certain temperature, which we call temperature. Turns out that this ring down time it takes for black holes to merge and form a single black hole is also h bar over kT. So this might seem like a strange coincidence, but it isn't. It turns out there's a deep connection between the quantum theory of black holes and the quantum theory of strongly interacting systems, which I really won't say much about here. But when we get to the SYK model, I may point to some reasons why that might be the case. Okay, so let me just go ahead and show you some experiments which give you this Planckian feature. So the plan of the lectures is to talk about various systems that show this Planckian dynamics, starting from fairly simple ones and eventually, hopefully, ending to things that relate to more modern materials. So here's one very beautiful experiment which really illustrates this very clearly. So this is just pure graphene. You just take single layer graphene. Today, of course, there's so many papers on So much work, also beautiful work on 2 layers, 3 layers, twisted and untwisted on different substrates. All of that is wonderful. But here, this is just graphene. Add half filling, 1 electron per site. So as we know, it has a Dirac dispersion, something we're going to review. And you measure its conductivity. So this is the conductivity measured at the terahertz frequencies by this group of Feng Wang in Berkeley. And so sigma prime is the real part of the conductivity, sigma double prime is the imaginary part. So the real part, looks like this. So when you first see this as a function of frequency, you would think, well, this is just some Drude peak. If you just take some Lorentzian peak, if you do the simple theory of electrons in metals, you get Drude theory, which gives you sigma in the Drude theory. Sigma is of omega is sigma naught times 1 minus I omega tau, where sigma naught is NE squared tau over m. So this is the famous Drude formula. So if you take the real part of sigma, sigma prime will become some sigma naught plus 1 plus omega squared tau squared. Okay, so that's called the Drude peak. It's a Lorentzian at 0 frequency. And the width of the Lorentzian is 1 over tau, which is some scattering rate. Okay, so now if you try to compute scattering rate in a metal, that scattering rate you can get from impurities, then that would be temperature independent. Or you can get from scattering rate from phonons. It'll have some power dependence on temperature, but it'll also depend on the electron-phonon coupling constant and many other energy scales. Similarly, the impurity scattering rate will depend on the impurity scattering potential. So there are all kinds of energy scales that appear by solving Boltzmann's equation for tau. Okay. So what's remarkable about this data is, first of all, if you look at the frequency scale, it's not frequency, it's just frequency divided by temperature. This is a purely dimensionless constant. And the data is taken many different temperatures, and it scales. It all falls on the same scale. So this means you can write this down in the scaling form. The conductivity is a function of frequency over temperature. I mean, you could also say that here, if you look at the frequency dependence, it's proportional to some function of omega tau. This would tell you, if I compare that to this data, that tau is h bar over kt. So that's your evidence for Planckian behavior. Doesn't seem to depend on anything, any material parameter at all. It's just temperature. So this is the certain universal aspect of very strongly interacting quantum critical systems. Now I say graphene, this is pure graphene. Why is that quantum critical? That's what the first lecture will be about, to show you why graphene does this. Even simple graphene is the system that shows this iconic behavior. There's another feature of this, which is in fact special to graphene and doesn't quite hold in other systems we'll talk about, is that the vertical scale is also universal. If you look at the vertical scale, it's just in unit of E squared over H, which is a unit of conductance, and where squared over H is in the integer quantum Hall effect. The integer quantum Hall effect is n E squared over H, where n is an integer, or fractional integers also in a fractional quantum Hall effect. So this is a zero magnetic field. There's no Hall effect or anything. System with an energy gap. But nevertheless, the scale is universal, it seems. It's just E squared over H, and doesn't seem to depend on anything else. So you say, okay, this is great, and this is just graphene, so why can't you compute this? So there are computations have been done. I'll show you some. Then that's the purpose of the first lecture, to show you how to compute this whole thing. It was predicted, but computed very accurate. It involves real dynamics, at finite temperature of a strongly interacting quantum system. And that's not something even the best computers can do very well because of sign problems and so on. But that's a field, I think that's the focus of this workshop, I guess. There's starting to be a lot of new developments that are now helping us compute such things, like, I don't know, some in machine learning, quantum simulation, and so on, all kinds of new ideas floating around these days. So my challenge to all these ideas is here's something simple. We know the Hamiltonian completely. I'll write it down soon. Compute this function and see if you can get the scale right, all these numbers. There's no arbitrary constants here. Everything is universal. Can this work out? Okay, yes. Yes.
Horizontal one, you're in the experiment, you say that you can change the temperature, right? Probably
Yes,
also frequency.
it's called the
So
electron.
when you say that also the vertical one is universal,
Yeah.
I mean, how do you play around in an experiment with the E2 over H? Is it possible even?
I mean, they measure
Yeah.
the conductivity in absolute units. And so, yeah, you're absolutely right. In fact, it's not entirely universal. It only depends, but it does depend slightly on the dielectric constant. So I think that's what I'm going to address in this talk is, first of all, how do you get the universality in the horizontal axis, which is much more universal and somewhat easier to explain. Universality on the vertical axis is something very special to certain systems in 2 dimensions, just like the quantum Hall effect. I'm going to talk about it, okay. It's not fully universal, I lied a bit, but there's certain models for which it is universal, which is how I'll talk about, yeah. Graphene is not quite a quantum critical system, but it almost is. Okay, so that's one example of Planckian dynamics. A much older one, so one consequence of this emerging picture of transport in graphene, because of the strong interaction, and something as simple as this, is that flow of electrical current in graphene is not as simple as in usual metals. In normal metals, when you think of electrical current flowing, you just think of it's some kind of diffusion of charge, and you can write down some diffusion equation, an Ohm's law, and that describes how spatially the current will flow. So what came out of this was something actually we predicted, that graphene should also display hydrodynamic behavior, that it's really more like a viscous fluid because of the very strong interactions. So there's a viscosity associated with graphene, and it can display phenomena in principle with current flow, which are more characteristic of something like water or something flowing in a pipe, which ordinary electrons and ordinary metals almost never show. That's because interactions are much weaker, and the motion of charge in metal is really much more diffusive. And viscosity requires momentum conservation between collisions, and that only happens in a strongly interacting system. So here I just asked ChatGPT, give me an example of hydrodynamics of graphene, and I learned about this beautiful paper from last year. I didn't know about it. So this is some kind of current flow with these little, in this strange geometry here of graphene on HPN. And then they're using NV center to test the distribution of current. So the colors are JX and JY. Yeah, they show the current in the X direction and the Y direction. Sorry, I myself should look at this. Right. So if you look at these 3 pictures, this is JX, the current at a given point. There's spatial information on the current. In the X direction, the Y direction, and this is some picture of the flow. And this is the experimental result here and here for JX and JY. This is if you solve a hydrodynamic equation, you get very much these patterns, and these different colors are supposed to represent the flow that I'll talk about in a minute here, and you can see this agrees very well. Whereas if you had diffusive flow in an ordinary metal, you get a very different current pattern. So if you look at the flow here, what you see here is that in the hydrodynamic simulation, you have current flowing, and because of the current flow, it drags the current in here, and because of the viscosity, this current now flows backwards. So the current in here is flowing backwards, whereas in diffusive flow, it doesn't do that at all. So this is a consequence, so there's kind of a vortex developing here due to the viscosity of the fluid. So if you did this experiment with water, this could happen under suitable conditions. And that's really the beautiful thing that they're seeing in this experiment. And this is one of the consequences of this very strong interactions in graphene. Okay, and there are many other experiments which have confirmed this idea. So that's a whole new, field that's very actively being studied these days. Okay, but actually Andy Lucas, my former student, would be a good person to talk about it if you want to know more about this. Okay, so then finally, of course, another system, not graphene, which I will, let's see, maybe not get to today, which is the high-temperature superconductors. And here, there's this strange metal regime near the highest DC, where there's also evidence for Planckian behavior. So this is, so why do we care about this? Well, very simply, any high TC material that's ever been found has a strange metal above its critical TC, above its highest TC. So if you want a theory of TC, you need a theory of the strange metal. It somehow seems to be deeply connected to strong interactions and also high temperature superconductivity. So one of the main properties of this strange metal is that the resistivity is a linear function of temperature. Okay. So now this is, this is just the DC resistivity, and graphene doesn't show this. Graphene doesn't have any linearity resistivity. But this is really looking at sigma naught, okay? So if you look at the sigma naught, and if you just take sigma naught is NE squared tau over M, and then you just assume the temperature dependence. So rho is then proportional to 1 over tau, which is proportional to temperature. So that's also this 1 over temperature. At least that you can see by looking at this. But then to see what the prefactor is just h bar or something else, you need to know about these numbers. So that's a bit more complicated, but people have studied that too. So this is an experiment where they looked at, I think they put a magnetic field in different directions and put a magnetoresistance. And after solving the Boltzmann equation, there's quite a bit of modeling. You finally can read off from the measurement of rho in a magnetic field what is tau in absolute units. So what they found in this paper was there was an isotropic component of tau and an anisotropic one. And the isotropic component, which is the red one, this is this dot here, that tau was h bar over tau was alpha times kBt, and alpha was 1.2. So again, so that's the Planckian behavior. You can see in the title of this paper in Nature from a few years back. Okay. But you can also do the kind of experiment that was done in graphene, which you measure the conductivity as a function of frequency. And that also has turned out to be quite complicated because the cis materials are very complicated. But here's the latest paper, which I think really fits a lot of data very well. So again, here we're not focusing on the sigma naught, but we're focusing on the frequency dependence. And they have a very particular way of pulling out from the sigma of omega this h bar over tau of omega in absolute units. So that's some very sophisticated analysis of the optics of this experiment done by these people. So this is the magnitude of sigma, this is the phase of sigma, they're plotting it really differently at different temperatures, from cold to hot. And then from all this data, they can read off the value of h bar over tau. And here it is as a function of both temperature and frequency. So what you find now, this is now tau written out, not the conductivity. It's h bar over tau, h bar over temperature of order, and f is a function. And this collapse of all this data as a function of omega over t, and then t times tau, gives you this very general scaling form. Again, Planckian dynamics. All right. There are several other examples, many other materials, that show behavior like this with this constant in tau, this constant here, alpha, which was called by alpha by the previous paper. Alpha seems to be around 1, but it could be 0.5, it could be 2 in different materials. It's not that universal, but it's close to 1. All right, so this is a feature of many, many important materials. And so my lectures are about, okay, let's find some models that look anything like this. All right, so that's the introduction, experimental introduction to things I've been puzzling about for many years. Any questions about the data anyway that I've showed you? It's very selective, but this is some of the best data, I think. All right, so this is my plan. So today I'll talk about something very much motivated by graphene, which is the Hubbard model of electrons on the honeycomb lattice. That's the first lecture. So that's not exactly graphene. Why? Because graphene is not a Hubbard model. It has Coulomb interactions, 1/r interactions, not on-site. But it turns out that, does make a difference, but not that much. And that's hopefully something I will get to at the end of the lecture. Okay, so that's model I talk about right now. Then I will go to what's called the SYK model. It's just a toy model of quantum matter without quasi-particles. As we'll see that, graphene all by itself is not really a metal. It's a semi-metal. It doesn't have a Fermi surface. But the SYK model is a compressible state where you can change the density of matter, so that's why it will be very useful to think about. And then I turn to the Hubbard model on the square lattice. Just a very small difference, but the behavior is completely different, where you get strange metals, and I'll combine insights from the SYK model to give you our current idea on what is the correct theory of the strange metal. So this is where I want to get to. This is the seminar on some more recent work at the very last, if there's time. I'll talk about something called the Yamaji effect that's only been seen a month ago, which is something we are pretty excited about because it's giving you, I think, a very encouraging signal that to understand the physics of the cuprates, you need spin liquid fractionation. Okay, and that's been a big debate in the community for 30 plus years. And I think this really comes down on the one side of the debate. All right, so let's get back now to let's do some work. Let's take the Hubbard model on the honeycomb lattice. Okay, so this is the honeycomb lattice, and we just take one electron per site. This electron in graphene sits in these p orbitals, these pz orbitals. The other covalently bonded orbitals are so tightly bonded you forget about them. That's a very high energy. The low energy is just the electrons hopping between these orbitals. So there's one electron per site on the honeycomb lattice, and the only interaction we're going to put in is the Hubbard repulsion. Okay, that's the Hamiltonian we're going to talk about for the next 45 minutes, maybe more. This is it. So there's only one parameter, which is u over t. So what is the ground state of the system as a function of u over t? U will be positive. I won't take u negative. Okay. All right. So at u equals 0, you ignore the interactions, and you just determine the band structure. So you get two bands, because there's two sites per unit cell, here, the green and the red sites. And there's two bands, and the bands have these nodal points, and there's a second band exactly the same, but flipped over, which meets these 6 points here in the Brillouin zone. So those 6 points are these 6 points here. So I'll derive this in a minute. And so these are the, if you look at the dispersion here near any of these points, the dispersed electrons has a Dirac form. It's basically EK is plus or minus VF squared, VF times square root of KX squared plus KY squared. So that's the dispersion at any one of these points, where K is measured from that point. So one thing to keep in mind that this, these green points, the Q1 points, are the same, because this is a reciprocal lattice vector, and the red points are the same. So there's only 2 points. So this is called a, this is a two-component Dirac fermion. Gives you this dispersion, this conic dispersion. Where is the cone? I haven't written it out. And how many Dirac fermions do we have? Well, we have 2 Dirac points, Q1 and Q2, and then we have spin. This has nothing to do with the physical spin of the electron. So there's 4 two-component Dirac fermions in graphene. All right, so this is how you do it. All the algebras here. So you take a Fourier transform on the A and B sublattices. The only hopping is between A to B. And then you introduce Pauli matrices. These would eventually become the Dirac matrices, tau, which are written in sublattice space. So, what particle physicists call Dirac spin, which is the different component of the neutrino or the electron, is here the sublattice. The sublattice index is the particle physicist Dirac spin. Our spin is a particle physicist flavor. It's just some flavor on the Dirac particle. So that's very important in the language to keep in mind. So when we talk about Dirac fermions, the spin, the particle physicist Dirac spin of the fermion is a sublattice index. This is A and B sublattice. And our physical spin, I guess they would call it a flavor or isospin or something like that. It's just some additional index. Okay, so now you introduce Pauli matrices that act in the Dirac space, the sublattice space, and then you go to Fourier space. So it's a 2-by-2 matrix because there's 2 sublattices, and this is what it looks like. It's completely off diagonal. A goes to B, so there's no tau Z here. Then you can just diagonalize this, of course, and get the energy eigenvalues. Right, and the energy, if you look at the energy eigenvalue, it would be this squared, square root of this squared plus that squared, and that will give you this plot. Okay, I'm sure you've all done this. All right, so now what we do is we're going to go near these points, the 1 point here and 1 point there, and take the low energy limit. So if you do that, you now introduce, so there's many indices here that you keep track of. So there's the spin index alpha, which just goes along for the ride. Then there's the A sublattice as Q1 and the A sublattice at minus Q1. And similarly, the B sublattice as Q1 and B sublattice minus Q1, which I call the sublattice index. I don't know for strange reason. No, so now the sublattice index is A and B, and the valley index, Q1 and minus Q1, becomes 1 and 2. That's the middle. Okay. So psi is to be an in-component vector, and rho is another set of matrices that act in the valley space, Q1 as opposed to minus Q1. All right, so you just take this Hamiltonian, and what you'll find is that both of these terms, this and this, vanish at these points, at Q1 and minus Q1. And because they vanish, you have to expand to next order, so you only get terms linear in K, and you put it all together, then you get this Hamiltonian, okay. So now the psi has 8 components. So the 8 components are sublattice, spin, and valley. And we take these 8 components and put various Pauli matrices that act on different sectors of this 2 by 2 by 2. So one set of Pauli matrices are the tau that act in sublattice space. Another set of Pauli matrices are the rho that act in valley space, and there'll be sigma, which will be the usual spin space. So you have 3 sets of Pauli matrices from which you can build any 8 by 8 matrix, and all 3 Pauli matrices commute with each other. So you have rho, maybe it's good to write that out. Tau, there are 3 Pauli matrices tau that act on sublattice. There's rho that acts on valley, and there's sigma, as usual, that acts on spin. And all of these commute with each other. So tau, rho is equal to 0, and that's all you need to know. Then you can build up any 8 by 8 matrix you want by taking products and sums of these matrices. Okay. All right, so after all that dust settles, then you get this. And now to make it more compatible with particle physicists, you define this psi bar, and then you introduce these gamma matrices here. You can just check this is a trivial change. And then finally, you can write this. Sorry, I'll come to that. What's happening?
Subir?
Yes.
Sorry. Just in 8, there is no sigma. There is only rho and tau. Did I miss anything?
Sorry? Yeah,
In 8,
there is no sigma.
There is no sigma.
So it's just sigma, everything is diagonal in spin.
Good.
Yeah. But there is a rho. Now that rho is kind of interesting. There's a rho sub z. So what is that rho there? Why is there even a rho? Well, the rho has to do with the fact, which has turned out to be very important in twisted bilayer graphene, that the chirality, the sense of this Dirac point, is the opposite to that. They have kind of some opposite chirality in terms of the dispersion and the Berry curvature, which is there's no Berry curvature here, but if you put a small magnetic field, you get opposite Berry curvature. Or sometimes people call it the vorticity. There's some vorticity associated with this. And these 2 Dirac nodes have opposite vorticity. And that fact has been key to many things in twisted bilayer graphene these days. It's not important here, but luckily we kept track of that. Anyway, it doesn't matter whether you put the rho z there or not, but for when you get to TBG, it's crucial.
In the end, we will have to worry only about taus, mostly, for what we'll be discussing today.
Well, or if you want to, I mean, at this level, so this is just very standard. Now you can see the Lagrangian. You can, if you want to, Lagrangian here for graphene in this very strange notation is psi bar minus I, psi bar, gamma mu, d mu, psi. So I've just done all of this to make that look just like a Dirac Hamiltonian that you might see in your particle physics textbook. Of course, there's a Fermi velocity also here. All right, so then I have an exercise which maybe, well, I don't know. We can come to this in the tutorial when we go through this. We'll come back to this. Let me do today's lecture. All right, so then I guess, okay, forget that. All right, so now we're going to add this. So far, we took the low energy limit of graphene and found this very simple Hamiltonian. So now we are going to add the interactions, okay? This interaction, U, okay. So suppose let's take the limit of very large U now. Okay, so what can we say at very large U? Well, at very large U, you're going to have exactly 1 electron per site because you don't want to put more than 2 electrons. You're at half filling, so the only thing you can do is put 1 electron per site. And then, what is the spin of that electron? So here, we have to do a mapping, which again, something we can do in the tutorial if you haven't seen it before. But if you have a single site, you have two sites nearby, and there's an electron here and an electron here. But there's also states at higher energy. There's the empty state and the doubly occupied state. Similarly here. These are just state labels, not actually where the electrons are. So the lowest energy state, it spins in different configurations. Now, if you hop an electron from here to there, if you hop this electron there, you will end up in this state. Okay, so that costs a big energy. This is energy U here. So it's going to just hop back. So if you do a second-order perturbation theory, you hop with T, you get an energy denominator U, and then you hop back with an energy denominator T. So this whole process, where you go there and come back, gives you T squared over U. This is the energy denominator in perturbation theory. This is the hopping matrix element. So you can eliminate this hopping process or by just taking this into account in perturbation theory. And then what you find is that there's some effective Hamiltonian, which is this Hamiltonian, where you have a nearest neighbor exchange interaction, SI dot Sj, where S is the spin operator, where J is 4T squared over U. So this is a standard derivation. It's in many books, including my book. I'm happy to do it in the tutorial, or yes, you have a question.
So in the structure of the spin that you find, you are considering that spin with actual spin?
Yeah, this is
electron?
actual spin, absolutely.
Plus the
We forget
orbital?
about Dirac. This is very far from Dirac.
Oh, that's the...
U goes
okay.
to infinity.
Okay.
U goes to infinity. We're back to the graphene lattice. There is no Dirac physics here at all.
Okay.
The charges are localized. It's an insulator. Sorry, that's the first thing I should have said. Now we don't have a semi-metal. We have an insulator at large U. It's an insulator with one electron per sites, and the electrons don't move. But their spins do couple, and they couple by this so-called super exchange interaction. J, which is antiferromagnetic, is positive in sign. It's 4T squared over U. Okay. So, why is it positive? Well, so let me draw the more picture here better. So you have these two sides. Let's say one is down and one is up. Then what can happen in it? So you have a matrix element T. This will hop. But the hopping conserves spin. So this will be up, down. And then it can hop back again, but can hop back to the opposite configuration. So it's possible to, so this is again T. So there's two hopping processes. You take an electron and hops there, but the other one comes back. So they have exchanged their spin, and that's why you have this S dot S interaction. On the other hand, if they're both ferromagnetic, nothing can happen. Pauli exclusion principle doesn't allow this to hop. So that's why the sign is anti-ferromagnetic. It likes them to be anti-parallel. That lowers the energy. Second order perturbation theory always lowers the energy of the ground state. And so that's why you get a positive sign here. And J is this. Okay. Yes? It's true in any lattice, anything, any dimension. It's a very general argument as long as U is bigger than all the T's. So this is any lattice here with any Tij. You just make U very large, and you're at half filling. Then the low energy Hamiltonian is this. Yeah. And even the factor of 4 is correct. It's true for any lattice. All right, so what does this tell you? So this tells you as a function of U over T that at very small U, you have a semi-metal with this Dirac fermion spectrum. I should have drawn this, so this is not on the slide. So this EK, if you draw it, it's this famous cone. as a function of k. And this is E. So that's the Dirac fermion. The Fermi level is here. And there's no Fermi surface because it's just a point. And so it's a semi-metal. It doesn't obey, specific heat much smaller than a metal because it only has a Fermi point. Okay, so that's what happens at very small U. And at very large U, it's an insulator. So you still now have to solve this problem, find the ground state of this Hamiltonian. So that's been studied a lot numerically, and now we know that the simplest answer, which is also the classical answer, is the correct answer, even for spin a half. And that answer is that the spins form an antiferromagnet. Okay, so it's an insulator, and one sublattice has spins pointing up, and the other sublattice has spin pointing down, and I see there's an error in my picture. What is this? Did I draw this? It's a ferromagnet. I'm sorry. I will fix that. This is some old slides that I took. Oh, gosh. I can't believe I put a ferromagnet when it should be an antiferromagnet. Okay, just imagine that the green sides are down and the red sides are up. Okay. All right, so now what happens in between? Okay, so we know now there's been quantum Monte Carlo study. This problem can be solved by quantum Monte Carlo. There's no sign problem. It's all been done to high accuracy, at least for the ground state. And what we know is that there is one quantum phase transition. Yes?
So you mentioned that the ground state and the antiferromagnet limit is Neal order.
Yeah.
But wouldn't you expect it to be some sort of singlet state of the whole lattice?
Well, I mean, that would be assuming a spin liquid. Yeah, so that's possible. But if you had, say, further neighbors, third neighbor interactions in here, in this Hamiltonian, that's possible, and that's something people are studying. I think there's people looking at Rydberg atoms on the honeycomb lattice. They have much longer interactions, and then maybe you get a spin liquid. But for the Hubbard model, we get this state. The nearest neighbor antiferro. People have studied both this full model or even this model with nearest neighbor couplings. And there's no doubt that you get the antiferromagnet. I mean, it's not really it has a broken symmetry. There's one vector that tells you which direction the spins are pointing. But if you took a finite system, the ground state is still a singlet. It's a singlet where all the spins rotate together. It's like a macroscopic singlet. So that we don't worry about. It's not, that's making a catch state or something. Usually it'll just pick out some direction. But this is embarrassing. I've drawn a ferromagnet. This is a slide from about 11 years ago. So I may be senile now, but I wasn't senile then. I don't know. And nobody said anything. Yes. Yeah, question.
So when we talk about graphene for the second example that we like talking, so it cannot happen in single layer graphene, right? Because we need to have repulsion to be much bigger than the
So again, we know. I mean, when graphene first emerged, there was a hope. But we know that graphene is somewhere here, but maybe not too far. But it's somewhere here. Yeah. It's definitely on the metal side. It need not have been. It could have been on the insulating side, but it's not. That's a question of numbers.
But if we modify these graphenes, can we reach such a thing, different layers?
If you could, I mean, what people normally do is put a substrate. Substrate has has a dielectric constant that reduces the interactions. You need to increase the interaction somehow. How are you going to do that? Yeah. The fine structure constant of graphene is still fairly small. If you make it large, it could become that. Yeah.
Thank you.
But yeah, of course, people have come up with very clever ways of accessing some. There are certain configurations in bilayer graphene where you put a magnetic field in some direction where you do indeed see an antiferromagnet. Yeah. It's a canted antiferromagnetic phase. Yeah. Okay, so now there's a phase transition. And in fact, it's a second order phase transition. We know from a lot of numerical work. It's a quantum critical point right here. And the rest of the lecture is to try to, not the rest, but to understand this quantum critical point. Okay, we want to understand what happens at low energies as I go across this phase transition. Okay, so the way it works is the following. We're going to do what's called the Hubbard-Stranovic transformation. So we take the Hubbard interaction. So we're going to start on this side, and we're going to try to do more than perturbation 3 in U. To some extent, we'll take U into account, to high order, so we can also get the other phase. So we're going to start here. Okay, so let's start with the Dirac semi-metal, and look at the interaction. This is another way to write the interaction. This is an exact identity where S is the spin on the east side. You can just work through, on each side you can do this. You can check this identity laboriously. Or you can say the following. You can say that if both sides are empty, then the left side is U over 4, because this will be 0, this will be 0. So that'll be U over 4. If the spin is 0, and so you get U over 4. If both sides are full, the left side will be 1 and 1. That'll again be U over 4. So if both electrons are present, the spin is still 0. So that's 0, and so U over 4. If one is up and the other is down, then this will be minus U over 4. And S, so if either, if spin up is present and spin down is not present, so then N up would be 1 and N down would be 0. This will be minus U over 4. And if only spin up is present, spin is 1/2. For spin 1/2, S squared is 3/4, S into S plus 1, 3/4. So you put 3/4 here, and this becomes minus U over 4. So you check it for all 4 states. There are 4 states, up, down, empty, and doubly occupied. And for all 4 states, you can check the identity work. That's the quicker way to check it. Or you just use lots of operator algebra. Okay, so we can write the Hubbard interaction here. Which came, e to the minus h in the partition function as minus 2u over 3s squared. So this is in the partition function, e to the minus beta h. I'm doing an imaginary time path integral. This is time, d tau. You get plus 2u over 3 times s squared on every side. And now I introduce the Hubbard-Stranovic transformation. This is an exact identity where if you do the integral over j, you just complete the square, then this exponent will just reduce to that, okay? It's without dropping various factors, there's a field j and SA, and then there's j squared. You complete the square here, then it becomes j plus some constant times SA whole squared minus some SA squared. Now this you can shift j by s and do the integral, so the integral is just some constant. So this disappears when you do the integral of some normalization constant, and you get the SA squared that was on the left. So this is the famous Hubbard-Stranovic transformation. We do it for every time and every site. So then the decoupling field J depends both on the sites and time. All right, so why this is so powerful? Well, this is powerful because now if you look at where the electron operator is, see this S here is just this electron operator. So if you look at the terms in the Hamiltonian, you have the hopping term, which is quadratic in the electrons. You have and then the only other place the electrons appear is in S. which is also quadratic in the electrons. So you have a theory of free electrons coupled by this coupling here to a scalar field J. Okay, all right, so yeah, there's a few steps before I get down to the last, and so let me now just carry out those steps on the board. So we initially start out with Z, and I'm assuming you've seen path integrals. If not, I can do it without path integrals too, but it'll be easier. So you have some dc of e to the minus h Hubbard. And that you can write as dc times dj, some vector field, exponential. And I'll leave out all factors here, the minus j squared with some factor. And then you have c dagger, some hopping c. And then you have j dot c dagger sigma c. Okay, so j depends on site. Okay, so what we're going to assume that so the j, you notice, couples to the spin. Okay, couples to the spin of each electron. Now what we know, so we want to, of course, if we do the integral over j completely, we are back to where we started. We're just back to the Hubbard model. We don't know how to solve. So we're going to say, okay, we know from my friendly computers simulation people that the most important component of the spins is the one, the antiferromagnet. Okay, so we're going to make a long wavelength approximation for J. We're going to write J, yeah, so it's going to be something like this. So we have J as a function of R. So J is a vector. It depends on the site, so R sub I. So we're going to say it's equal to some vector field phi, which also depends on the site R sub I, times e to the I k dot R. Okay, so this you can always do, where k here is the antiferromagnetic wave vector. So it's whatever you need to get up on one sublattice and down on the other sublattice, okay? And the approximation we're going to make is exactly the approximation, similar to the approximation made to get the Dirac fermion description. We went from the hopping Hamiltonian to this, and now we're going to say is that phi varies very slowly. It's almost a constant, but not quite a constant. We're going to include fluctuations of phi in both space and time, but I'm going to expand in gradients of phi. All right, so what happens then? Well, first of all, if I do the free electron part, which is this part, then I get the Dirac fermion that I already showed you. Then let me take this term here, and take its long wavelength limit. So that involves a bit of algebra. You just insert this in there, and you keep track of all the indices, and so on. And I did this once in my life, and this is what you get. Okay, so you get psi bar with some matrices. In this case, there's a sigma matrix here. That's the spin, sigma A, coupling to phi A, and there's a coupling lambda. Okay. So there's one very interesting thing about this, which didn't have to happen. So this has to do with these strange bar notation. So the bar notation is introduced so that you have these gamma mu's, and the gamma mu's are supposed to commute with all the rhos and all the taus. So the gamma mu's are a Dirac spin, or the sublattice index. And relativistic people have told us this is relativistically invariant. And now you notice, you look at this thing, it doesn't, fortunately, involve any gamma mu. It doesn't involve any tau explicitly. So this thing is also relativistically invariant. It's a psi bar psi with some flavor in these matrices that we don't care about. So this turns out to have higher symmetry than you might think. So it was a surprise that graphene was relativistically invariant at low energies. This is a second surprise, which is also very pleasant, at least to field theorists, that even the interaction, at least this particular interaction, to the Néel order parameter is also relativistically invariant. It just means that we can now call up our field theory friends and learn a few things from them, because there is no gamma here. If you took some other order parameters, like nematic order parameters or different charge density wave, there's all kinds of possibilities in TBG, and most of them are not relativistically invariant. But this is the simple one that is. Okay. Anyway, so that gives you this. So then there's J squared. Okay, that becomes phi squared. Then what about the other terms? Well, I just put them down by symmetry. Well, let's just put in some gradients and some interaction. So this is, phi now, this phi has become our Landau-Ginzburg order parameter. So this is like our Landau-Ginzburg theory order parameter. This is just the LGW order parameter. And what Landau told us is when you have an order parameter, you write down a theory, which is grad phi squared plus r phi squared plus u phi fourth. This u has nothing to do with the Hubbard u. This is just to stabilize the interaction. So what we are saying is that we have this complicated Hubbard model at high energies, but there are lots of high energy modes. But close to this phase boundary, close to this phase transition, I can do some RG. I integrate out those high energy modes and write down some low energy theory that only takes into account the things that are essentially zero energy near the critical point. So what's essentially zero energy? Well, there's the Dirac fermions. There's zero energy everywhere in the semi-metal, so we keep them. And then there's phi, because you're going to break the symmetry, it's the order parameter. So these three terms here is exactly the Landau-Ginzburg theory in space-time. Not space, but it's exactly the Wilson-Fisher theory whose solution won them the Nobel Prize, at least Wilson the Nobel Prize. To that, I add Dirac fermions, and then this coupling, and that's called the Yukawa coupling. So this model is sometimes called, this particular type model is sometimes called the Yukawa model, which was studied in 2 dimensions for particle physics for different reasons. Also Nambu and others. Yeah.
Many questions. Hopefully some of them are helpful. So the information that you have on honeycomb lattice comes only because you know that there you're going to have antiferromagnetism. That's the only point where you use the fact that you are on honeycomb lattice to do this approximation.
I think I used it almost, well, first of all, to get Dirac fermions, I needed honeycomb.
Okay, so but that information will be in the free part, right? In the psi, d mu psi. So for the interaction,
but also for this thing not to involve a gamma mu, somehow it turns out that this is one particular order parameter that doesn't involve the gamma mu.
Right.
That also depends on the honeycomb structure. I mean, Néel state is pretty friendly to relativistic invariance, and you get it in many other cases also. And the square lattice with pi flux, pretty much the same thing will hold.
So you're saying there are hidden details in these calculations that if I had another lattice supporting antiferromagnetism, I would have not got this Lagrangian.
Well, I mean, the issue of relativistic invariance doesn't even arise when you don't have Dirac fermions.
Of course.
My next lecture on the square lattice in zero flux, this is the part that's, this doesn't even exist. This doesn't exist on the square lattice. So if that doesn't exist, I can't even talk about relativistic invariance of anything else. But even on the honeycomb lattice, if I took some other order parameter, like C6 symmetry breaking, for example, that also breaks in TBG, this will not be relativistically invariant. And then this is a more complicated theory to analyze, on which we have many papers, but it's a mess. Yeah, there's another question there. Yes.
Just continuing on his question, you said about the direct fermions,
Yeah.
that you needed the honeycomb to get like that extra degree of choice, that you can be in one lattice or in the other sublattice. If I have other structures that are not honeycomb, but I also have this two sublattice structure, could I get this same Hamiltonian?
I don't know. You really have to work it out. I mean, you have to see whether not every bipartite lattice has Dirac spectrum. You know, honeycomb is one of them. The square doesn't. Square is also bipartite. It doesn't have a Dirac spectrum.
The square is?
Well, it's a bipartite lattice. Okay, you can, maybe you can take an AB square lattice, you know, for example. That doesn't have any of this. So somehow the same transition in the square lattice is complicated. It's a lot simpler. Yeah, all of this, which is why I'm talking about it first.
Okay, thank you for.
Yeah.
So with the Yukawa coupling term, it seems like we have some valley rotation symmetry, right? Because I could just rotate the rho z around the z-axis.
Yeah.
Does that matter? Is that?
Right. So this has some emergent. I mean, there's an 08 symmetry in here. So if you go to real fermions, God knows how many. You have 8-component complex fermions. No, 4 components. So it's 08. There's an 08 global symmetry. So forget about the Dirac part. So there's really 4-component complex fermions, complex Dirac fermion, which is 8 Majorana fermions. So there's an 08 global symmetry, which is, now picking the phi A breaks the 08 global symmetry down to 03. So in fact, the full symmetry is 03 cross 05. It has a lot of symmetries here. Okay. Yeah, there's an 03 cross 05 symmetry of this low energy theory.
Okay. Thank you.
Yeah. There are papers, I think Herbert and various people have been exploring all these huge symmetries, this model. Yeah.
We are giving priority to students always. I think
so when you integrate out the fermions there,
yeah,
you won't get any like Landau damping term, or
so we're not going to integrate out the low energy fermion. We integrate out only high energy fermion. So everything must be analytic. For Landau damping, we're going to compute that. That's what the theory will compute for us. We've not done. We keep the low energy fermions. You know, here's our Dirac spectrum, where these states are occupied, and those are empty. You integrate out holes over here and electrons over here, but this you don't touch. You have some cutoff, so there's no question of any damping. Everything is analytic. I mean, understanding the Landau damping is the whole purpose of this exercise.
Thank you. Subir, I do have one question. So what is the physical interpretation of this phi sub I? So you're
it's just the antiferromagnetic order parameter.
But it's completely disconnected from the capital phi. I mean, at some point when you take the expectation value, the other phi, so the other side.
You mean the J? So so phi is the low energy limit. It's just the low energy limit of J. J and phi are the same thing.
Yes, and the phi.
Yeah. So what you see here, right? So these are conjugate values. So this electron spin is conjugate to J. So you can then see if you insert a source for J, that the JJ correlation function is basically constant, the same as the SS correlation functions.
Yes.
Conjugate variables.
Yes. No. The big phi here. The how do you call it? The below.
Oh,
this one. This
psi.
This psi. Yes.
That's just the electron.
Exactly, but the electron is connected to the, I mean, the expectation, there is a connection between the electron and the spin order parameter. Or
that's this one here. So psi bars, this is basically the, so, yeah. So there are 3 different ways of writing the antiferromagnetic order parameter. Mm-hmm. So the antiferromagnetic order parameter, AFM, it's something like, you have C dagger, I, sigma, Ci, expectation value goes as e to the k dot r times some quantity here. And then you can also have ai will be e to the I k dot r times some quantity, which is the order parameter. Or you can take basically phi a. This is the same. This thing here is practically just phi a. And this thing here is practically that psi bar rho z sigma a psi.
Exactly. So there is a connection between these two, or
Yeah. So if you just
okay.
if you go through the steps, in fact, that's what. So if you do this, if you go through all these steps, okay, on C dagger sigma C, at this wave vector, you will get exactly this. I've saved you the trouble of doing that, but that is the calculation you have to do. Right.
Okay.
The physical, this is the physical expectation value. This is the only physical thing. If I'm talking to an experimentalist, I have to give them a number for this. Do some hard work through all my transformation to translate my number to their number, depending on which one I compute. I mean, there's all kinds of transformations here. I just have to undo them. And well, they only know what meant. You can do neutron scattering, for example. I mean, they can measure spin. Yeah, yeah, exactly. They measure this. Yeah.
So the J is just an artifact that you use in the theory to do calculations.
Well, these are, yeah, if you wish, you can think of it that way. I mean, it's just much easier to work now with these variables for the theorists. But, I mean, let me just show that a little bit then. For example, how is J, why are these even connected to each other? Which is actually that equation 12 over there. It follows from equation 12. Okay, so suppose I want some correlation function. So I have my initial theory is just S squared, okay? Now, so if I was working with this theory, I would add a source term, let me call it K dot S. So I would do this, I'll get a generating function, which will be integral over S of e to the minus this thing. And I will take derivatives of this, dk, to get any correlation function I want of S, because K conjugate to S. Okay, so I just keep this term, and I put it in there. So what I notice is that this becomes K plus J dot S. Okay, so now when I do the Hubbard-Strauss transformation, I'm going to get, after the Hubbard, I'll get exponential minus whatever. Okay, you have to, it's a little bit more complicated now, but basically you'll get some function of K and S. So now you have to take this with this and just work it out. And to first order, in fact, S dot S correlation functions are the same as J dot J correlation function, up to some factor that you can work out from this transformation. Okay, sorry if that's a bit of a mess, but I can point you to a paper where all the factors are written down. It's just a matter of doing Gaussian integrals over and over again, that's all. And using this identity. You always add some source term. So you put a source to the thing you want to measure. You keep it through all the transformation. Then you just compute this after all your transformation, and you will get what it is in terms of the new fields. That's all. So, yeah.
Okay. Well, certainly it's a beautiful idea. So this is kind of working because you are on a honeycomb lattice, and somehow you are assuming or you're sure that you actually have one phase transition, right?
Yeah, yeah, absolutely. This is all, without the benefit of so much computer work, I would never know this works. I would not know. This is just a guess, as far as a theorist is concerned. But now that I know that my computer friends have told me there is a second order phase transition between a semi-metal and an insulating antiferromagnet, then I'm very confident this is correct.
Yeah, so somehow then it doesn't look like, to me, it's going to tell us where actually the phase transition is going to happen, right?
It'll give you some mean field estimate, just like any old, Landau theory on the Ising model gives you some mean field estimate. You can do the same here.
Yeah. And the final question is that, I could check this also in the internet, but wasn't the Gross-Neveu model was like interacting fermion power 4 without this bosonic parts?
So it's the same. So there's Gross-Neveu model is psi bar psi 4. You do the Hubbard-Strutanovich transformation, you will get this model, which is sometimes called the Gross-Neveu-Yukawa model for that reason. So you just do exactly this transformation on the old Gross-Neveu model, you will get this model, which is, I should have called it the Gross-Neveu-Yukawa model. Again, this is from a long time ago. People were still calling it the Gross-Neveu. Now it seems to be called Gross-Neveu-Yukawa in the literature. And I don't have the tech files of this, so I can't correct them. I couldn't find the tech file. I found the PDF.
Like the type in the antiferromagnet. You have to redo it, right? On the lattice.
That is easy. That's a figure I can fix.
So because you're getting a lot of questions, I will not give you a signal. You go ahead till 11 without any break.
Okay. All right. All right. So this is the phase diagram as a function of S now. Now we have a new field theory, where S is my tuning parameter, not T over U. And in this field theory, has the same phases. It has phi equal to 0 when S is negative, and phi S is positive, and phi not equal to 0 when S is negative. And now you can do something also very interesting. You can now put phi a constant. Now if you take a phi a constant, put that phi a constant. Now this is your Hamiltonian, this is your Hamiltonian. You can diagonalize it and get the band structure. And what you find in the band structure is the band structure of massive Dirac fermions. Basically, now your dispersion in the insulator becomes EK approximately. I may not get all the factors right, but if you work it out, it's kx squared plus ky squared plus phi squared. So there's a mass term here, which is just phi itself. So that's another sign that it's all relativistically invariant, because even in the ordered phase, you've now got a gap. Your Fermi level is in the gap. It's an insulator or a semiconductor. And this dispersion is exactly of that form, at least at small momentum. Okay, so finally, we are now ready. We have all the tools to address this critical point. Okay. All right, so now we really have to go back to the field theory and analyze it by RG. So I'm not going to do that, and again, depending on the question and where we get, we can go through some of the RG analysis in the tutorial section. So let me just say what happens, roughly. So if I just take the scalar sector, that's the Wilson-Fisher theory, and we know what happens there. So there's so in the Wilson-Fisher theory, so this is just grad phi squared plus S phi squared plus U phi to the 4th. This is basically the same theory you would use to get the phase transition of the thermal phase transition of the Ising model in 3 dimensions. Here we're in space-time, not in space, but it's essentially the same thing. Ising would have 1 component, there are 3 components. Doesn't make that much difference in the structure of the RG flow. And what you find is that at some critical value, S equals SC, you get RG flow. If you look at the RG flow of U, it goes to a fixed point at long distances to UC. So this is what Wilson and Fisher taught us, that at the critical point of just the scalar theory, there's a renormalization group invariant fixed point which has scale invariance and also conformal invariance. I'm not going to go into all the consequences of conformal invariance, but that's what you get here. And then you have this term lambda, so there's another term here, phi psi bar psi, and then you have psi bar d slash psi here. Well, if you work out the RG in various approximation, you get exactly the same answer, that lambda also flows to some lambda c. So in the end, this is a very beautiful, not just relativistically, but even a conformally invariant fixed point. It's like a conformal field theory. And then you can use also many other powerful tools, including insight from anti-de Sitter space to understand the low energy limit of this point. Okay, but we're not going to use that. All right. So this is, all right. So it's some complicated, it's a new type of many-body state that we haven't studied very much. It's gapless. It does, in fact, has no quasi-particles. Let's see, how do we see that? Okay, so yeah. So how do you do this calculation? So well, you can try to compute, for example, the fermion-Green's function. And if this was free particles, you will get this answer with eta equals 0. So what the RG people have taught us is that you get some anomalous dimension when you have a strong coupling fixed point like this, which just gives this power from 1 to 1 minus eta over 2, and eta is called the anomalous dimension. And you notice that now this term doesn't have any poles, it has only branch cuts, and that's an indication of the breakdown of quasi-particles.
Subir?
Yes.
Yes. Before you go forward, what is the critical U you get from RG? The value.
Okay, first of all, this U has nothing to do with the Hubbard U, so which U are you asking about?
Yeah, I was asking about the Hubbard U, whether, how do you
RG, I don't know. I don't know. I mean, in the end, the first thing you do is just do Hartree-Fock. The answer from Hartree-Fock will also give you a critical U. That is pretty much the same U you will get by this method. The same thing as Hartree-Fock.
So you would get something mean field-like.
Yeah. Now you can improve that with RG,
Okay.
but then that will depend on the cutoff, and I don't think anybody really has done
Worried
that.
about the value.
Yeah, I mean, there may be other methods to compute U. You can do some 1 over U expansion or small U expansion and try to get it. I don't know if people have done that. But numerically, you know it quite accurately.
Yeah. I was just curious how it compares with the numerical value.
I can ask ChatGPT, it'll tell you. Why don't you just
Okay, thanks.
I think Fakhr Assad has some simulations where the numbers are there. What is the critical Hubbard U? All right, so at this point, there are no quasi-particles. And so if you took the imaginary part of the spectral function, instead of having a pole, you get this continuum spectral function, for example. Okay. All right, so now, what I want to now relate to the experiment that I showed you at the beginning of this lecture. I want to sit at this point now. I want to sit at this critical point. I'm going to sit here and compute the conductivity. First of all, I will do that at 0 temperature. And then you do it at finite temperature. And that understanding, there's a whole long story there of how this turns out to be one of the first examples of, Planckian dynamics. Because of this strongly coupled fixed point, now you just compute the conductivity that they're measuring, they have measured now. What is it going to look like? Okay, so you just do the simplest thing. You just do Kubo formula. So I'll do it with free Dirac fermions first, and then we look at the effect of interactions. So here's all the graphs worked out because it's all relativistic. It's quite easy. This is the current correlation function in the Kubo formula. This is the propagator of the electron. I've even put a mass term corresponding to having some order, but in the end, you put the mass term to 0 just to make life simple. Yeah, there's the mass term. This is what you get. And then you find it's purely transverse, and then you breathe a sigh of relief because it must be transverse to conserve current. So that tells you did the calculation properly. There's all these gamma matrices you have to work through. I will, there it is. And then the Kubo formula tells you that you have to take this limit. And this is in units where h bar is 1 and E is 1. So, there are various coupling constants here. There's a Fermi velocity. There's the Fermi velocity, and what else? There's nothing else for Dirac fermions anyway. But you find in the end that the conductivity, which is K00, this is the dynamical conductivity, sigma of omega. This is not quite right, is it? So this is sigma of 0, sigma of k, 1 over k squared. No, that's correct. What happened? Oh, yeah, that's fine. Okay. So you do all of this. This at 0 temperature, you compute the conductivity, and you find everything drops out because this is this is free Dirac fermions, so it's also a conformally invariant system, and you find this remarkable result that sigma of omega, this is at t equals 0, is 1/4. Okay, so now you have to put back in physical units. So in physical units, you forgot an E squared, and there's an H bar. And then conductivity, we like to measure in units of H. So you put a 2 pi over there. So in the end, when the dust settles, it's E squared over H times pi over 2. So that's a very interesting result, that the conductivity of free Dirac fermions is in fact just pi over 2. That's all I did was evaluate a one-loop graph. Okay. Then you think a bit more deeply, based upon all the conformal invariance and the fact the current is conserved, and you're looking at the current correlation function, which has universal amplitudes near a critical point, and so on. And then you can conclude that this is actually part of a more general result, that at any conformal field theory, if you computed the conductivity, including the Gross-Nouveau fixed point, it'll be some number. It's a pure number times E squared over H. For free Dirac fermions, it's pi over 2 times E squared over H. But for any conformally invariant fixed point, it'll be, this pi over 2 could change, but that's the value here. Okay. Yes, this is all for 2 plus 1, thank you. Free Dirac Fermi, massless Dirac Fermi in 2 plus 1 dimension give you this number for the conductivity. Now let me just show you, here's a measurement of, this is the high frequency conductivity. Remember, so we're working at 0 temperature, but the more precise way to say this is for omega bigger than T. It's pi over 2, and this is a measurement by Dmitry Basov and Hawk-Stomer. Pi over 2 E squared over H is 1. That is exactly what you see in graphene. You see it. You see exactly pi over 2. Of course, graphene is not a free Dirac fermion. It's not even a Dirac fermion. All kinds of dispersions at high energies. It's got Coulomb interactions. Yet it's pi over 2. Since I'm out of time, let me explain that part. I was going to do a lot of other stuff, which I guess I'll do after the break. So how do we understand this? Well, if you take graphene, this is the full Hamiltonian for graphene. Okay, now you have, at low energies, you have the Dirac fermion, and there's your Coulomb interactions, depending on the dielectric constant and so on. So this theory has only one free parameter, dimensionless parameter, which is the fine structure constant, which is E squared over epsilon VF. H bar is 1 here. Okay. So now, if you can now, you can also now ask what is the RG equation of alpha. So what we found was that for here, the interactions were due to this lambda. The lambda went to a fixed point. But this long-range Coulomb interaction actually doesn't have a flow like this. Alpha has a flow, it just goes to 0. So that's what we know about graphene. It very, very
Sorry,
slowly
Subir,
goes.
what is epsilon?
Huh?
What is epsilon?
Dielectric constant.
Okay, good.
So it goes to 0. And this is another thing we can do in the tutorial, to actually compute this. I think we could do this. But it goes to 0 very slowly. You know, it's minus alpha squared, not alpha. So if you solve this equation, roughly you will get that alpha is like 1/1/4 log of temperature. Something like that. It goes very slowly to 0. But eventually it does, or at high frequency it goes to 0 also. So that's why, in fact, whoops, you see this at high frequency. Okay, so that's the high frequency measurement, but this was an infrared measurement where they measured the high frequency part. This measurement here is not high frequency. This one I started the whole lecture with. This is low frequency. Frequency is smaller than KT. This is done by terahertz, whereas the other one's done in infrared, which is much higher frequency at this roughly the same temperatures. So for this, we can't use this. And maybe I'll come to that. I will now want to talk about the conductivity frequencies below temperature. That's where you get the Planckian dissipation. This is more like conformal behavior at high frequencies, which you can simply understand by perturbation theory, actually. And there's actually quite a few papers by Igor Herbert where he's computed the corrections at high frequency, and there's 1/log omega corrections, which maybe have something to do with this fall off here. I don't know. Probably not. There's other effects here.
Subir,
Yes.
just to help everyone to orient with the importance of the result. So this high frequency conductivity that is set to raise to constant alpha under RG going to 0, I should contrast it with more regular behavior that should do what? So why, let's say, this is striking compared to, let's say, more conventional materials?
Well, I showed you the Drude form for conventional material. Sigma is sigma naught 1 plus omega squared tau squared. It would just go to 0. So basically, it'll go to 0 is 1/omega squared. And then eventually, at some high frequency, you'll get some interband transition. So if you had a metal, where you've got a metal with some occupied state, and you got some other bands over there. So at low frequencies, you get this part, and that will give you just the Drude peak. Eventually, at high frequency, you'll go to the other bands, then you may get some mid-infrared peaks. But you won't get this constant or large frequency range. That's prediction of the theory, and that it should be, and even the number comes out right. So it's quite amazing. It's just free Dirac fermion to begin with. The entire calculation is right here. Okay. Yeah, that's it. Okay, then the calculation at finite temperature is a bit more complicated. No one did it before I worked it out, and it's much more complicated. And anyway, I'll come to that after the break. So now we break for half an hour, and then I start again? Yes. Okay.